Hello, welcome to episode 3 of this Device to Cloud series. And in the last episode, I have tried to expose this little device, tried and succeeded, to expose this little device to the great public internet and allow myself to switch the LED on and off. Now, that was, as I call it, the 4 patterns of device communication. That was a command. And the way I implemented this was to give the device a local address on this network, listen on the port, and then expose that out through my NAT firewall here at the house, take the public IP address, register that in DNS, and then have the client talk to my gateway, addressing number 1, addressing number 2, then go and talk to my device. 2-stage addressing, need to have a well-known address in the network. I also need to have an IP address here. I need to register that with DNS. So I need to go and solve the addressing problem to actually get to that device. And then also the device needs to deal with unsolicited traffic inbound, and that has all of its problems, as I'm going to go and explain in a little bit more detail today. What I could also do is, if the device sat on Powerline, Zigbee, some other protocol, then I can go and have a local hub device. The local hub device then goes and acts as the gatekeeper kind of for my device. The third approach that I didn't explore in code is IPv6, and combinations of the first 2 approaches. Either I expose the device directly, I give the device an IPv6 address that can be reached from the rest of the world without the NAT thing. That removes one stage of addressing. Or I use a protocol like IPv6 bridging to wireless personal area networks like Zigbee. And there's protocols for this which allow kind of bridging for IPv6, where those devices then also become directly addressable without having that intermediate device. That's all nice and fine. And a lot of companies seem to see that as the future, but what that doesn't remove is that the fact that the device then still listens on a routable network, and that comes with a number of constraints, and that's why I'm saying that's still a very unhappy place. And I'm going to elaborate on that a little bit before I show you the alternative to this. So first of all, if I have a device like this, and it actively listens on the network, it needs to be able to defend itself. It can get some help at the link layer. So this device is now linked to a network, and it does so in this case through a network cable and plugs into an Ethernet hub, but it could also do that through wireless and plug into my wireless network. There has to be some protection. Now the Ethernet hub here is protected by my presence. Nobody else can go and plug into that hub, at least not without getting past me, and you see that's a problem. And if it were on the wireless network, they would have to get my WPA2 protection, also called IEEE 802.11i, and that is a fairly capable protection. It's not broken yet. Other than, for instance, web, the protection that was previously used on Wi-Fi is still used on Zigbee, and that, of course, is completely broken. Why does that matter, the link level protection? Because if I have access to the link level, I can go and send unsolicited frames to everybody on the network and effectively flood the network. And if you are implementing a security system based on a network, and you're actuating, or so you have sensors who are reporting that people are coming into the house, and that's raising the alarm. And if you saturate the network in a way that the sensors can no longer report what they're seeing, or the alarm can no longer be raised, that's a good first stage attack to taking out all the valuables out of a building. So what you shouldn't do is accept connections from unknown link layer clients, and the way you do that is by choosing capable infrastructure, because that's happening on the infrastructure level. The device, however, is on the hook for anything that's routable traffic beyond the link layer. So everything comes to it through the network transport application layer. That's something that the device will have to go and deal with, and ultimately at all of those levels, may that be IPsec or TLS or then application level protocols, which have to be implemented kind of in the device stack, then the device is on the hook if it listens to authenticate each connecting client. If you are doing this for the purpose of, let's say, phones which connect to your house, and you want to go and connect from my phone and my wife's phone and my tablet, my wife's tablet, and the whole family kind of wants to have access to, let's say, the security system or the home entertainment system, whatever, then all the devices which are hooked up to this, if the devices are listening, would then either have to rely on a security server that's in the house, so there's now an extra device that kind of needs to sit there on the side, or need to implement security, need to implement a notion of accounts all by themselves. So there's authentication required, and accounts means there's security, there's key material associated with that. In the simplest form, obviously passwords, but more typically keys, maybe symmetric keys or asymmetric keys. So there's a lot of effort. And then, of course, each communication path needs to be individually protectable as well. What you don't want to have is the same model as you have it for the link layer protection, where we're basically protecting everything that is in a relatively limited scope of a house with a single shared key amongst a few set of devices. Once you have devices which are unroutable protocols, so they're bridging across a broader area, and there's a risk that one of those devices that are connecting to this system gets compromised in some way, then you will have to go and revoke all the keys to keep the system secure, then have to go and distribute all the keys, so that gets fairly complicated. So for that, you want to have both for authentication, an individual model for keys per client, and also an individual way to go and protect the end-to-end communication. So that all starts getting pretty difficult if you listen. If the device acts as a server, then those things are not really easy. The reason why the device needs to do that is because it needs to triage legitimate from illegitimate traffic. We need to assume, specifically for security systems, but also for every single system that can actuate something, that can cause something in the physical world, that someone will go and try to break it. And if it's only walking up to some device, going to a lamp and switching that lamp 50 times a second, it will break. So protecting those devices and having proper security is something that's required, and triaging bad traffic from good traffic requires that you have authentication, some form of authentication in place, and that's something you have to do. You're required if you're actively listening for traffic, because you need to triage that traffic out. Also, if you are listening on the network, if you allow inbound connections and you're doing that triage, you need to record that triage result somewhere, so that you can actually take a look at the log and see whether someone is attacking you, and also need to share that with someone. So you need to make this transparent, you need to go and aggregate it in some place, and you need to go and review who's trying to get to you, because if you don't watch that someone tries to get into your door, well, then they have all time in the world. They can try 100 million times, and you will never know if you don't write that down. And this device here, that little device, doesn't have the room to go and log all the intrusion attempts. And of course, and that's something that's a concern for all of the small devices, if we want to hook them up to the network, is they need to retain operational health while they're being attacked. A server, big iron in the cloud, that can easily do this. That can go and say, after 500 concurrent connections, I'm going to shut the door on the front, and I'm going to report that out on the back, and it still has enough capacity to go and defend itself. That little device doesn't even have an operating system. Everything runs on bare metal in a single thread. There's no swapping of registers, any of those things, which means if you saturate that device, then that device is saturated, and then you have taken it out. And if that's an alarm sensor, you're out of luck. So devices should typically, if they're not capable of defending themselves, not listening on the network. The alternative to that is that they don't. So that they will only selectively connect to a place, and that is outbound. And then have someone help them with all that defense work, instead of having to implement that on the device itself, which keeps the device cheap and kind of outsources a bunch of the hard part of the security story to an external service. I'm using a cloud gateway here, so I'm moving this into the cloud. I'm moving this into Windows Azure because typically that makes a lot of sense. It makes a lot of sense because what I want to talk to the device from is this phone. That this phone is connected through UMTS, 3G, LTE, if I have a good day here, or GPRS, which means this is on a public network, and I can go to the cloud very easily and go and connect to my device through a cloud gateway. And typically most of the clients that I'm going to have to switch a system in the house is going to have that connectivity. If I want to keep this locked away from the public space, I can certainly go and take the gateway and also implement a gateway like this inside of a private network. Kind of make it a private cloud solution if you like, if I want to build it something similar on the factory floor or in a larger intranet, then you can go and certainly do this. But for residential solutions, having a cloud gateway is actually a optimal solution if you want to go and connect from arbitrary devices which have visibility to the internet, even if you're connecting from your own house to devices in your own house. If you have internet connectivity, you can do this. If you're worried about online, offline, if you have flaky internet connections, obviously you can also have an extra cloud gateway, extra gateway that sits inside of the house, inside of a machine. But then you need to have a local hub of some sort that can live in the house, and then also there pulls energy. So it's a trade-off between how much do you rely on the internet connection for those kind of capabilities and how much do you want to have this as a local capability in case the internet fails. So the model is the device does not listen for unsolicited traffic, and the connections are device initiated and outbound. With that, the port mapping through the NAT device is also automatic and outbound, and you can have about 60,000 devices from a single IP address, because that's how the port mapping works. Probably you can actually have more than 60,000, just a little bit more than that. And if you really had more than those, then like you have a larger building, then it's certainly feasible that you can have more IP addresses from your ISP and more outbound connections, and then that accommodates 60,000 more. You can go and do some more sophisticated routing, certainly in bigger commercial environments. Sorry. The nice thing about this is, as all connections are now outbound, as the device now only does outbound connections, there's no inbound ports, which means there's no surface area you need to worry about for unsolicited inbound traffic. What's also nice is the addressing problem completely goes away. Nobody except for the party you're connecting to, the cloud gateway, really needs to know the IP address that you're at. The IP address gets automatically mapped into the NAT. The NAT knows that now, and then it gets connected to the cloud gateway. The cloud gateway knows the NAT address, so that's all automatic. That route automatically gets established, and this all works very nicely with IPv4, so you don't need to deploy IPv6 for that. And then as a result, you have the gateway, you have a public address, fully defensible. You have a server as large as you want it in the cloud, and that then allows you to implement whatever security mechanisms, whatever first line, second line of defense you want to go and build for the device. And the way you talk to the device is you go to the gateway and you talk to the gateway. This is a very similar principle, by the way, that as we're implementing that on the Windows Azure Service Bus Relay, which functions after this principle, and also the Windows Azure Service Bus broker works with that principle. Outbound connectivity only, no inbound connectivity required. But instead of showing you the product, what I'm going to show you is a very pedestrian way of implementing this very easily. So I'm going to switch into Visual Studio here, and I'm going to show you the implementation of this. And we're going to go and take a look first at the Arduino file. Here I have the MAC address again. I don't have an IP address registered as I had in the previous example. So let's take a look at the setup. I'm going to go and start the Ethernet client just with the MAC address. What's then going to happen is that an IP address is going to be automatically acquired using DHCP. There's no need for a configuration. The router doesn't need to know this device. So which means we've now already radically simplified the setup, right? The device can basically just show up on the network and be part of it, and it doesn't need to be registered. There's no configuration that needs to be happening. So this is already simpler. Then I'm flashing the LED to see that it's connected. And now in the loop, if I'm not connected, I'm going to connect out to the cloud host. So this is cvledblinker.cloudapp.net for the moment for me. And once I am connected, I will go and write the device ID out to the network. This is device number 1, so it's going to register itself as number 1. And I have this embedded in this code just for simplicity. And now if it's connected, what I'm going to do is I'm going to read commands that are coming up from the cloud, that are being sent to me from the cloud. And I will go and read them. And if it's a 0, then it's a ping. Then it's a notification. It's not a command. It's a ping that says the server is still here. And the reason why we need this is that there's intermediaries on the path, NATs, firewalls, etc. And they still want to know whether there's still activity that on that socket, whether they want to, can throw away the socket. And therefore, I'm sending that ping. And then if it's number 1, so I send this every 55 seconds. And if it's 1, then I'm going to turn the LED on. It's a command, so I'm writing the ACK down and or up, depending where the cloud is. And then if the LED is off, if I read a 2, then I'm going to also write the ACK and turn the LED off. So that's the Arduino side of this. And let's go and take a look at the cloud side of this. I'm going to start with the Windows Azure configuration. That is here. I have 2 endpoints. I have a device endpoint, that's what the device connects to. I have a control endpoint, that's where we connect to with HTTP. Let's look at the implementations of that very quickly. I have this sitting in, there's 2 hosts. One is the LED Blink service, that's the thing I deployed to the cloud. That's the test host. The test host is a local test harness that I can go and use to go against this, because the local simulator for Windows Azure, or emulator for Windows Azure, is actually firewalled against traffic that comes off machine and only allows on machine traffic. And so I built this little test host around it, and the server is very minimal. I'm not claiming it's best practice. It's just it's an interim solution, because we're going to make this more sophisticated. So I've chosen the most simple path to the functionality. So there's the front and the back. So we're going to take a look at the control endpoint first. That is our web API. So this is using the ASP.NET MVC web API. I'm creating an API controller that has an HTTP put. HTTP put is being invoked with that ID, and then with the state, and then I'm calling the switch method. It's a static method. And if that's okay, then I'm returning the OK code. Otherwise, I'm returning the not found. And the switch method is part of the switch server, which I'm going to show you. The switch server, that's actually the thing that implements the control endpoint. The device endpoint. Control endpoint, we've just seen the interface, the implementation of it. And I can go and quickly show you. This is a HTTP, it's a web API self-host inside of a worker role in Windows Azure. The reason why I'm not putting this into a web role or into a website is because they're kind of kept alive by HTTP traffic. What we want to do here is we want to park socket connections in here, and there's a bunch of extra configuration I would have to go and do on either of those. So I'm using, for simplicity, for right now, I'm using a web role and kind of mushing this all together. We're going to separate this out. I'm going to make this clean and wonderful, but for the time being, we're going to self-host the HTTP endpoint in here. So that's the controller name. We call the switch controller, so this is going to be switch, and then the ID is the ID of the device. So this is where the control endpoint is hosted. That's what I'm talking to using HTTP. And now let's take a look at the device endpoint that the device talks to. That's the device endpoint here. Make some room. Making a new TCP listener that listens on an endpoint. It starts, has a backlog of 10 pending connections that can be piling up. Then I'm starting the ping timer universally, irrespective of connections. Every 55 seconds it pulses and causes a callback into the ping connections, and that writes into all open sockets a ping frame, a 0, and flushes it out. And then I'm accepting inbound connections. If there's inbound connection, I'm going to go and configure that inbound connection to turn off nagling. Nagling is buffering up multiple bytes until the frame is full, but here the protocol is just 1 byte. So we're going to go and flush it straight to the network. Set the receive timeout to 10 seconds so that if there's a connection error, we're going to detect it early. Get the stream out, read the device ID that was written into the socket as the device connects, so that's where I'm reading that out. Here, turning that into host order, using that as the connection ID, so I'm registering all current connections in a dictionary, in a concurrent dictionary, and then I just keep reading off the buffer the responses effectively to all the commands that I send, and if I get an acknowledgement to it, to a command, then I'm going to set a synchronization event, which I'm going to use down here. And that is the switch method. So again, here's the controller. If I go and set a put, I'm calling this method switch. And that method switch then tries to see whether a connection exists for a device with that particular ID, gets the socket, so that's how it matches the socket. And then basically just goes and writes out asynchronously that frame. The on frame is a 1, the off frame is a 2, and then waits for the signal to be raised from that reading loop, which will then go and unblock here with a true if that's in the timeout. If the device doesn't answer within the 10 seconds timeout, then we're going to terminate the client connection, and we're going to eliminate that connection out of our pool. So that we're going to raise a 404. We're not going to go and come back with a true here. And so we're going to get a not found. I deployed this into the cloud. You can actually get this code at this address. It's sitting on GitHub. I also have the same address, obviously, also at the bottom of this post here on channel 9 and on YouTube. And now we're going to go and see this alive. So I have the device sitting here. The device is nicely connected already, so I can go and turn it off. So now it's off. And you see I'm talking to the cloud here. I'm talking to my service that's running in the cloud. I can turn it on again. And now I'm going to do something interesting. I'm going to go and disconnect it. And I'm going to try to turn it on again. Well, obviously now the device will not react. So now we can wait for 10 seconds. The connection has not been terminated yet. Nobody knows about this yet because the NAT hasn't forgotten about this yet. The client has not forgotten about this yet because we have not yet set the ping. But now, after 10 seconds, it knows the device is gone. And so if I do this now, then it's fairly quick in realizing that it's not there. And now I'm going to go and connect this again. I give it power again. That's exactly what I'm doing. So I just ripped it off the network by just pulling the power out of the machine. So now it just booted back up, and I can easily turn it back on because it aggressively connects out. And I didn't need to know anything in these entire mechanics than the ID that I gave the device, the number 1. The rest is kind of automatically in this code. I didn't have to deal with IP addresses. I didn't have to deal with any of that sort. Didn't have to deal with IPv6 or any of that thing, because it all rendezvous very nicely in ultimately what ends up being a mapping hash table inside of my app, and that obviously makes that very simple. Now, one further concern certainly is, first of all, how do you get this secure? we haven't done anything about authentication and all those things yet. We're going to have that in a future episode. One more immediate concern that I want to address is what happens if that device is occasionally offline? If the connection here were not a network wire, but if that were a Wi-Fi connection or as a GPRS connection that could go in and out of coverage every once in a while, but I still want to send some commands to the device and eventually want to get them, that we can also solve, and also solve very elegantly once we have this baseline setup of having a cloud-based gateway. And how that works, I'm going to show you in the next episode.